Okay, good morning, everyone. Three announcements before we get started. First of all, the first instructor question is due today, and the second one has been released. Make sure you don't confuse the two. The second announcement is I have office hours in person on Fridays, straight after the lecture. This is in the ACW room. It's AQ 4145. So after Friday lectures, I know that several people tend to come up after the lecture and ask me questions. If you can go to the office hours on a Friday, please do and ask your question there. And I'll try to prioritize people who can't make the office hours after the lecture. So if you can make the office hours, please go and ask me your question there. If you can't, then come to me after the lecture. And the third announcement, I have an apology. I wrote down the wrong definition of scalar projection. So we are all human, we all make mistakes. Unfortunately, I copied these notes from someone else, and I never actually learned scalar and vector projections when I was an undergrad. So I never used them. Anyway, the correct definition of the scalar projection is here. So there was a squared term in the denominator, but that's incorrect. It should not be squared. So what we do, if we want to work out the scalar projection, we do u dot v, and if we're projecting v onto u, then we divide by the length of u. So what does this mean? If you do the scalar projection of a vector onto itself, if you do u dot u, that's going to give you the length of u squared, divided by the length of u, and you just end up with the length of u. So the scalar projection of a vector onto itself is just the length of that vector. Okay, so you're characterizing the amount essentially of a vector that is pointing in the direction of that vector. And then if we want to work out the vector projection, if we're using this scalar projection to define the vector projection, then we need to divide by the length of u. So this was actually defined correctly, the projection here previously, because it was written as essentially u dot v divided by length of u squared. That's the same. It's just if we're going to use this scalar projection as this c here, then we need to also divide by the length of u. So all the questions that had projection, the vector projection in were correct. I believe there was a question in one of the self-study questions which I've corrected. And if you have got any of the OQ questions wrong about scalar projections because of this, please don't worry, I will account for it when I do the final grades and make sure that no one's penalized for it, okay? So once again, my apologies for getting that wrong. If you do spot any typos, please let me know and I will check them and amend them as quickly as possible. There also might be occasional typos in things like the lecture videos. If I've noticed any afterwards, I put them in the description of the lecture video. So before you watch any of the pre-recorded lectures, just have a quick look at the description, see if it says there's any typos, okay? And the course schedule page will always have the latest set of notes, okay? So if you think there's a typo, just have a quick check on the course schedule page to see if someone's already alerted me to it, okay? Any questions? Nope. Okay, so today we are going to be talking about matrices, and it's one of the very few lectures where we're not going to be talking really about biological examples. The reason is because matrices are super important mathematical tools, which we'll be using time and time again. And for many of you who haven't met matrices before, just a quick show of hands, who's met matrices before this? Okay, so there's a smattering of people, but most of you haven't, okay? We're going to be using these pretty much throughout the course. We use matrices to store data. So for example, if I want to have all of your grades in a big table, just like a spreadsheet, I'll have a row for each of you and then a column for each of your different grades for different assignments. That is essentially a matrix. Okay, we've got rows and columns, but we use them to solve linear systems of equations. We're going to be talking about those very soon. We use them to do population models. We'll be doing lots of population models, say how individuals age through different classes. So different rows and columns will correspond to different age classes. We use them to understand the long-term behavior of more complicated models later in the course. So for example, more complicated epidemic models, we can use matrices to understand whether an epidemic is going to take off or whether it's going to die out. Okay, so they're super important things. We need to understand what they are, how we can manipulate them. So this, along with the next couple of lectures, we're going to be talking a bit more about the mathematics and a little bit less about the biology. but that's a little bit of a necessary evil to make sure you guys are comfortable with working with matrices. Okay, so what is a matrix? Like I said, matrix is just essentially a collection of rows and columns. We can, in theory, use them in more than 2 dimensions, as in, you can have rows, columns, and whatever else, and we use these to store data on computers in that way. So be familiar with what the rows and the columns are. We often use this notation here. We'll use, say, a capital letter for the matrix itself, and then we'll use this indexing notation of a lowercase letter with the row and then the column. So A11 is the first row, first column, A12, first row, second column, and so on. Vectors are essentially special matrices. They're just either a row matrix or a column matrix. How do we deal with matrix addition and scalar multiplication? Well, we just do everything element-wise. So just like we did with vectors, we combine the same components together when we're adding them. And when we're doing scalar multiplication, you just multiply everything in the matrix by that scalar. Okay, so that's pretty straightforward. It gets a little bit more complicated when we start thinking about multiplication involving matrices. So we can multiply a matrix by a vector. And the key thing here is that the order in which we do things matters. So if we have 2 scalars, A and B, we can do A times by B, B times by A, that's fine, right? If we've got 2 matrices, capital A, capital B, or a matrix A and a vector V, it matters the order in which we combine those things, and we can't necessarily write them, or rather the product isn't necessarily already always defined. So A times by V might be defined, but V times by A won't necessarily be defined. How do we actually do that? Well, if we have a matrix that has m rows and n columns, and we have a vector which has n rows, then we can combine these things. So we end up with an m by 1 vector when we're taking a matrix and a vector product. So the key thing here is that we are taking this bit here, this n, has to match this n here. Okay, if these are 2 different numbers, then our result is going to be undefined. And then what we get out of it has dimension m by 1. Okay, so down here, when there's a 2 by 2 matrix times by a 2 by 1 vector, we check that these inner parts have the same number, so they're both 2s, we're fine. And what's our result going to be? It's going to have 2 rows and 1 column. That's matrix vector products. As I said earlier, vectors are just special types of matrices. So the same rules apply when we want to do matrix products. So if we have a matrix A that has m rows and p columns, and a matrix B that has p rows and n columns, then first of all, we check if we want to do A times by B, that this P matches this P. Then we end up with an M by N matrix, because we take those outer ones. So check the inner parts, and then your dimensions of your result is going to be determined by the outer parts. How do we do the actual multiplication itself, assuming that it is defined? Well, you remember the rule, go along the rows and down the columns. Okay, so what do? If I want to work out the first element of this matrix, of our result, AB, I take the first element here of A on the first row and multiply it by the first element in the first column. But then I add that to the second element in the first row times by the second element in the second row. Did I say row? I meant column. And here, if you take the third element of the first row, multiply it by the third element of the first column of the second matrix, add these things together. You notice we're essentially taking the dot product. If we have these 2 vectors and we transpose the column vector, we take the dot product of these things, and that gives us the result. So this is why we have the dot product here. So just remember, work your way along the rows and down the columns. There's a few properties here that I'm not going to dwell on. one of the key things to remember though, is that, like I said at the beginning, if we have scalars A and B, multiply them together, it doesn't matter whether we do A times by B or B times by A. But if we have two matrices, A times by B might be defined, but B times by A isn't necessarily defined. We'll talk a little bit more about some of these examples today. The reason that one might be defined, but the other isn't defined is because we care about the, if we have an M by P and a P by N matrix, those P's have to be the same that are on the inner product. Okay, that is everything from the pre-recorded lecture. Can I just have a show of hands who watched the pre-recorded lecture? Great, you guys are great. Any questions about any of that material before I go on to the problems? Yes.
For question 2 and 3 for the self-study question, may I just ask like why 2 would be scalar but 3 is a matrix?
Let me just have a quick look. Question 2 and 3, sorry.
Yeah. I just want to know why 1 is scalar, but when we do the other way, that one is
It's because V is a row vector and U is a column vector.
Yeah.
And when we do U times by V, are you able to go to the office hours? Are you able to go to the office hours? This might be a okay, that's fair. Okay, so when we do V times by U, so let's just work through this one. If we do V times by U, we've got this. So here, this is defined, and we have to do 2 times by 1 and add it to 3 times by minus 1. Okay, so we just end up with a scalar. If we do it the other way around, if we do 1 minus 1 times by 2, 3, here the first element is going to be 1 times by 2, but that we've already gone along the row. There's only one thing in the row, and there's only one thing in the column for the second one. If we think about the dimensions of these things, up here, we've got a 1 by 2 and a 2 by 1. Okay, so these inner parts, the 2's match, and what we get out of it is this 1 by 1. Okay, when we do this one here, when we change the order, here we've got a 2 by 1 and a 1 by 2. Again, this is defined because these inner parts here both have the same number, but our output is going to be a 2 by 2 because the size of our output is determined by the things on the outside. Okay, so it's a really good question. If we do 2 vectors times together, if one's a row and one's a column vector, if it's defined, in one case we might end up with a scalar, in the other case we might end up with a matrix. Okay. Any other questions? That's okay. Let's work through some problems then. Okay. First of all, we're just going to do some hands up or shouting out answers here. So we've got 2 matrices, A and B. Very quickly, very easy. What are the dimensions or what are the sizes of matrices A and B? So what's the size of matrix A? 2 by 2, great. Matrix B, 3 by 3. Okay. These are also referred to as square matrices because they have the same number of rows and columns. Okay, I'm just going to get you guys to shout out the answers to these things. So what are the entries of the matrices? So I'm going to work my way down this. So A11, A12. Let's try that again. A12, 3. Okay, so this number here, the first one is the row index, and the second is the column index. So 1, 2 is the first row, second column. A21, A22, B11, B22, B23, 1, 7. So second row, third column. Is that one? B32. Hi. Okay, great. Nice and easy. Okay, how about we'll do some addition and scalar multiplication. Again, apologies that this is not really a biologically focused set of questions, but we kind of have to get familiar with how we manipulate matrices, and this is the quickest way to do that. Okay, so there are different matrices here, A, B, C, and D, and we've got these things we want to work out, these different additions or scalar multiplications of these matrices. So first of all, Can you just shout out, is A plus B defined? No, okay, it's not defined because we need to add each of the components of A to the components of B. We've got 3 columns here, but we've only got 2 columns here. So when we get to this element here, there's nothing to add it to. Okay, so this is not defined. So A plus B is not defined. A plus D, defined or undefined? Defined, yeah, they've got the same dimensions. B minus D, they're not defined, right? Because if we want to, say, add this element here from B to an element from D, there's nothing here. So it's undefined. Minus 2 times by B, defined, yeah, it's just a scalar times by our matrix. And 3C minus 2B, defined again. So it doesn't matter that we've multiplied B and C by scalars here. They still ended up with the same dimensions. Okay, have a quick go for the next few minutes of just working through some of these. I might not have time to go through all of the answers, but just have a go at practicing it. And I'll walk around if you have any questions to ask me about how we do scalar multiplication of matrices or addition or anything else you can. Okay, let's run through some of these. So remember, A plus B is not defined because we don't have the same dimensions. A plus D, A and B both have the same dimensions. So let's just write this out. We're going to have this element here, 2, added to this element here, 6. We're going to have 2 plus 6. The next row, the next column, we're going to have 0 plus 3. So 0 plus 3. 7 plus 4. Minus 5 plus 5. 4 plus 9. And then 3 plus 8. So remember, we just work our way across the columns or down the rows and just go element wise. So you should have ended up with, unless I've made a mistake, 8, 3, 11, 0, 13, 11. Have a show of hands who got that? Great. That's A plus B. B minus D is not defined. Minus 2 times by B. So minus 2 is just a scalar. So all that means is we're just going to take minus 2 and multiply it by every element that's in B. So the first element of B is 4. So we're going to do minus 2 times by 4. So we're going to have minus 8. We've got minus 3 as the second element. So we have minus 2 times by minus 3, which is 6. Third element is 0. Working way down into the second row, we have minus 2, minus 10, and 2. Again, have a show of hands who got that? Great. And then the final one here, we've got 3C minus 2B. So here what we're doing is we're multiplying C by a scalar 3 and then subtracting 2 times by B. We've already worked out what minus 2B is, so we don't have to work that out separately. So what are we going to have here? 3 times by C. So we're going to have 3 here from 3 times by 1. I'm also going to do the subtraction at the same time. So we've got 3, and then we're going to have minus 2b, so we're going to have minus 8. 3 minus 8. We are going to have 3 times by 2, so we're going to have 6. And then we're going to add it to 6 because we've got a 6 down here. And then 3 times by 3, so this is this 3 up here. We're going to have a 9, and we're going to add it to 0. That's this 0 down here. Yes? It is subtraction, but we've already worked out what minus 2b is. So this is the same as doing plus minus 2b. Yep. But important to think about signs. So that's good. Right, second row. So we've got 0 from C, minus 2 from down here. And we're going to have minus 3, minus 10. And then 2 minus 0. So, sorry, 0 minus 2, I should say. I'm sorry, 0 plus 2. God, Friday mornings. 0 plus 2. So you should have ended up with minus 5, 12, 9, minus 2, minus 13, and 2. In case I've made a mistake. I'm terrible at mental arithmetic. So if I do make a mistake, please do let me know. Who can I have a show of hands who got that? Okay, that probably means I did it. Good. Okay, so scalar multiplication, pretty straightforward. Addition, subtraction, pretty straightforward. We're just working through things element-wise. Now let's think about some things that are going to be a bit more applicable to us, matrix vector products. So we will be constructing lots of matrix vector products because a lot of examples that we'll be going through, our variables of interest will be defining by vectors, and then our matrix is somehow manipulating that vector. Okay, so we'll talk a little bit, one of the future classes, about what matrices do to vectors in a more geometric sense. And they can be thought of as things that move a vector around. So what I mean by that is if you have just say R2 and you've got a vector, imagine that as just an arrow pointing from the origin to a point. If we multiply that vector by that matrix, what we're essentially doing is we're just moving it to a different point. So we're moving everything in that space is kind of getting twisted around, say, or rotated, depending on what type of matrix we have. Okay, so there's like a geometric interpretation of what a matrix does to a vector. Don't worry about that too much now, but it comes to be important a little bit later on. But we can also just think about it in algebraic sense. So what is, if we times a matrix by a vector, what is happening to each of these elements here? Okay, so as before, let's just work through each of these and see which of these are defined. So we've got these matrices A, B, and C, and we've got two types of vectors here, U and V. Like before, just shout out, A times by U, is this defined or undefined? Undefined, right, because A is 2 by 2, U is 3 by 1. This number here does not match this number here, so the product is not defined. So this is not defined. B times by U, defined, yeah. We've got a 3 by 3 and a 3 by 1. These two things match. Can anyone tell me what the size of the output is going to be? 3 by 1, great. So we take this element here and this element here, or this size, I should say, and that gives us our output. Okay, C times by U, defined or undefined? Defined, okay. So here we've got C, which has 2 rows and 3 columns, and U, which has 3 rows, 1 column. Again, these numbers match. The size of the output is 2 by 1. Okay, you guys seem to have the hang of that, so I'm not going to dwell on it. The others, I will let you work through and post the solutions. Okay, the next question is to evaluate all the allowable matrix vector products from above. So let's just focus on, well, you can work out which ones are defined as well, but obviously this first one here is not defined, so you don't need to do that one. Work out BU and CU and any of the others that are defined. Again, I'll walk around and make sure that everyone understands what these are. I will leave this page up. Okay, so work out all of the allowable matrix vector products that are written here between 1 and 6. Remember, when we're working this out, we go along the rows and down the column to work out whatever entry we're working out from our vector. In all of these cases, we're going to end up with a vector, right? Because we've got a matrix times by a vector, which always gives us a vector. Okay, let's see how you guys did. So let's just quickly check which of these other things are defined. The only one here that's defined is this AB. These ones here aren't defined. A has dimension 2 by 2. B has dimension 2 by 1. So these match, and we're going to get a 2 by 1 vector. And the other things we've got are BU and CU. So we're going to have a 3 by 1 vector and a 2 by 1 vector. So how do we work these things out? A few people have asked about interpretation of these things or different ways in which you can do them. There are essentially 3 different ways you can think about this. If I just write this out, we've got 1, minus 1, 1, 0, 2, minus 2, minus 3, 3, 0, 3, minus 2, 1. Okay, so one way, and the way that I tend to think about it is I work along the row, down the column. And I go for the second one, I go along the second row, down the column. Third row, down the column. That's the way I tend to think about it. Another way you can think about it is that this here is a row vector. This here is another vector. I can take the dot product of these things, and that gives me the first element. Likewise, I can treat this as a row vector and do the dot product. I can treat this as a row vector and do the dot product. Again, that gives you the same output. The other way you can think about it is something that was done in the lecture notes, which is taking each of these as column vectors. You take this column vector, first column vector, multiply it by the first element, add it to, let's do it in a different color, add it to this as a column vector, multiplied by the second element, add it to this column vector, multiplied by the third element. Whichever way you find easiest is fine, okay? As long as you end up with the right answer, that's okay. You should end up with, regardless of which way you did it, 6, -6, and -15, I believe. Can I show of hands who got that? Fantastic. Okay, the next one was C times by U. So here we've got 5, 0, 2, -1, 4, 1. 3, -2, and 1. This time we've got a 2-row, 3-column matrix times by a 3-row, 1-column vector. The inner parts match. The outer part is going to be, get rid of that. The outer part here is going to give us a 2 by 1 vector. So note here that even though we're multiplying, our vector is the same as before, we've changed our matrix and the dimensions of our output are different, okay? In this case, we'll end up with a vector that should be 17 -10. So really the key thing here is that even though we've got this same vector here, I'll just color it in, this is the same vector in both cases, it's the dimensions of our matrix that determine the dimensions of our output. Okay. The third one, if you did do it, I'll just jot it down here. AB was equal to 3, 3. Have a show of hands, you got all of those right? Okay, great. I think that was a question there. A little bit louder. Sorry. Okay, so if it's a vector times by matrix, you're going to have a row vector rather than a column vector, okay? Because again, we need to work our way along the rows and down the columns. I'll leave that as an exercise for you guys to think about what it would mean if we tried to do a vector times by matrix. As long as you end up, say, if you had a 1 by 3 times by a matrix that was call it a 3 by 3, right? These inner parts here, they match, so it's defined. If I tried to do this with a column vector that was 3 by 1, these inner parts aren't defined anymore. They're not the same, so the product's not going to be defined. So we can do it, but it has to be a row vector. Okay? Any other questions? No. Okay, only a few minutes left, guys. Just do a quick true or false. If A times by V, A is a matrix, V is a vector. If A times by V is equal to 0, then either the matrix A or the vector is 0. True or false? False. Okay, we know this from our dot products as well, right? That we can have, it's very similar to that because we're using essentially the dot product to combine these things. We don't necessarily need to have a 0 matrix or a 0 vector to get the product of the matrix and the vector being 0. If a matrix product AV is defined, and so is BA. True or false? False again. I'll leave it to you guys to come up with some counterexamples. Again, there are some counterexamples in the solutions. Think about how you might come up with a counterexample to these things. Okay, if both AB and VA are defined, then they have the same size. True or false? False again. Okay, so again, think about what a counterexample might look like for these things. A vector matrix product VA is never defined if A is of the size 3, 4. True or false? False. As we've just seen, if we use an appropriate row vector, then we can have VA being defined. No, these are just any matrices. Oh, sorry. Yeah. Okay. The last thing, we've got a few minutes left, so maybe we'll skip over. Okay, let's work through it. There's only a few. Okay, so think again. We've got some different matrices here. We've just done matrix vector products. Just make sure you guys are familiar with matrix products as well. So it's the same basic principles, but rather than just having one column because it's a column vector, we're going to have multiple columns. Okay, so essentially the same thing, but we work down the first column and then we just work over to essentially the next column and the next column. Okay, so we've got these different matrices here. AB is what size? 3 by 3. B is what size? 3 by 2. C is? D is? 2 by 2. Okay. I'll work through these. What is, either tell me the size of it or tell me if it's not defined. AB. AB is 3 by 2. AC? AC is not defined because this 3 doesn't match this 2 here. AD? Not defined. BC? BC. So the inner parts here are 2. The outer parts are 3. Okay. So the inner parts match, which is fine. The size of our matrix is going to be 3 by 3. CB? 2 by 2. So this time the inner parts are going to be the 3s. So we've switched the order around. They match, and the output size is going to be defined by the outer bits. So this time it's a 2 by 2. Across there. CA, 2 by 3. And DC, 2 by 3. Okay. As I mentioned the other day, you can use online tools, things like Wolfram Alpha. If you're not comfortable with doing some of these calculations, or you think you need some more practice, use those if you need to. There is also this question at the end. I'll post the solutions to that as well, to working out those matrix multiplications. Have a good weekend.